Lesson 5, we're going to be multiplying polynomials. I'm going to start with some simple polynomial multiplication, and as we work our way through the lesson, the examples will get a little bit more complex. I'm going to start by multiplying monomials, one monomial by another monomial. Then we're going to talk about the distributive property again, and then we'll finally talk about multiplying binomials. So let's start by multiplying monomials. Remember, a monomial is just a polynomial with just one term. So in this first example, we're multiplying the monomial 5x by the monomial x cubed. And really what we're doing here is just using the property of exponents that we've been talking about in the last lesson. This is 5 times x cubed. Remember that x can be considered as x to the first power. So the rule for multiplying powers with the same base is to add the exponents. So I have x to the 1 plus 3. That gives me 5x to the fourth. Let's try it again. Now I have the product of a second degree monomial, negative 3 times x squared, times a fourth degree monomial, 2x to the fourth. Now here I'm going to write out a lot of steps just to kind of show you what's happening. What I'm going to do is I'm going to use the commutative properties and the associative properties to rearrange the factors in this multiplication. So I'm going to look at the factors of the two coefficients and then consider the factors of the two powers of x. Multiplying the coefficients, I end up with negative 6. Multiplying the powers of x, once again, I'll be adding the exponents, and I'm left with negative 6x to the sixth power. Now I have a product of 3 monomials. In the last example, we saw that we could multiply the coefficients and then multiply the powers of x. Let's do that here. 5x times 2x cubed times negative 4 times x squared. Multiplying the coefficients, 5 times 2 is 10, times negative 4 is negative 40. Multiplying the powers of x, I have x to the first times x cubed times x squared. Adding those exponents, 1 plus 3 plus 2, I end up with negative 40x to the sixth. Now, in a previous math class, you've probably worked with the distributive property. We're going to be doing a lot with the distributive property in this lesson. So multiplying any polynomial by a monomial is just an application of the distributive property. Let's see some examples. We're going to find the product of 5x times the binomial x plus 2. I can use the distributive property here. I'm going to multiply 5x by the first term in the binomial, x, and then add the product of 5x and 2. I'm going to write this all out for the first example. So I have 5x times x plus 5x times 2. 5x times x is 5x squared. Multiplying 5 by 2 gives me 10, and I have just one factor of x in the second term. Let's do it again. Negative 6x squared times the binomial x plus 2. Again, I'll be multiplying both terms in the binomial by negative 6x squared. So I have negative 6x squared times x plus negative 6x squared times 2. Negative 6x cubed, I added the exponents, x squared times x, that gives me 3 factors of x. For my next term, the coefficient is negative 6 times 2, or negative 12, so I'm adding negative 12x squared, which is the same as subtracting 12x squared. I'm going to do it again. This time, my monomial factor is on the right rather than the left. I can still use the distributive property. I'm just going to work right to left rather than left to right. So this is going to be the product of 5x to the 4th times 3x to the 6th minus 2x to the 5th times 3x to the 6th. Both terms in the second expression are now just the product of monomials, which is how we started this lesson. In the first term, multiplying the coefficients first and then multiplying the powers of x, I end up with 15. X to the 4th times x to the 6th is x to the 10th. I added the exponents 4 plus 6. Then I'm subtracting the product of 2x to the 5th, 3x to the 6th. That gives me 6x to the 11th power. Now if you need to write out a few more steps at this stage of the game, you can do that. You can recall the exponent rules as you're using them. On the other hand, you might just be able to go right from the first expression right to the simplification. Write down as many steps as you need at this stage of the game. Let's do it again. Now we're multiplying a trinomial by negative 4x cubed. Negative 4x cubed times the trinomial x squared minus 2x plus 1. I'm going to distribute the factor negative 4x cubed to each term in the trinomial. So negative 4x cubed times x squared, I have a coefficient of negative 4, and I have 5 factors of x. Multiplying negative 4x cubed by negative 2x will give me a coefficient of positive 8, and I have 4 factors of x. Finally, multiplying negative 4x cubed by 1 just gives me plus 4x cubed. One last example. 2x to the 4th times the polynomial x cubed minus 5x squared plus 6x minus 1. Now I'm going to distribute the 2x to the 4th factor to each of the 4 terms in the polynomial inside the parentheses. So 2x to the 4th times x cubed is 2x to the 7th. I'm adding the exponents. X to the 4th times x cubed is x to the 7th. Multiplying 2x to the 4th by negative 5x squared gives me negative 10x to the 6th. 2x to the 4th times 6x is 12x to the 5th. And finally, 2x to the 4th times 1 is just 2x to the 4th. Now we're going to look at the problem of multiplying binomials. Binomials are multiplied by using the distributive property twice. Let's see an example. We're asked to find the product of x plus 5 and x plus 2, two binomials. Now what I'm going to do here is remind you of how to do a simpler problem. Here's the problem we're working on here. But imagine that the first factor is just a constant, say 8. Well, we know how to use the distributive property here. We multiply each term in the second binomial, x plus 2, by 8. We can do the same thing if our first factor is not a constant. Here's the problem we're working on. Now our first factor is x plus 5 rather than just an 8. But I'm going to multiply each term in the second binomial by the factor x plus 5. So I've just taken this factor x plus 5 and multiplied it by each term in the second binomial. Now when we're doing the simpler problem here, there's some more steps. I need to simplify, and you need to go ahead and perform the arithmetic, the 8 times 2. Similarly, there's more steps involved in the more complex problem we're working on now. Look what I have to do now. I have to use the distributive property a second time. I need to distribute this factor of x to each term in the factor x plus 5. Similarly, I have to distribute this factor of 2 in each term in the factor x plus 5. So I have x squared plus 5x, that's the first, what I came from the first term, plus 2x plus 10. So you see I've used the distributive property in 2 steps. Finally, combining like terms, I have x squared plus 7x plus 10. So using the distributive property twice, I found an equivalent expression, x squared plus 7x plus 10. So now, since I did so much work there, I'm going to kind of confirm that these two expressions are equivalent by just checking these two expressions for some different values of x. I'm just going to create a table to organize my work. So in my table, I have the two expressions, x plus 5 times x plus 2, and the equivalent expression, x squared plus 7x plus 10, that I found by using the distributive property twice. I'm just going to arbitrarily choose some values of x. I'm going to choose a negative value of x, perhaps x equals 0, and perhaps one positive value of x. And what I'm going to do is just evaluate these two different expressions for these values of x. I should be getting the same result. So if x equals negative 2, I have negative 2 plus 5 times negative 2 plus 2. So that equals 3 times 0, which equals 0. When I evaluate x squared plus 7x plus 10 for x equals negative 2, I should get 0 as well. So when x equals negative 2, we have negative 2 quantity squared plus 7 times negative 2 plus 10. That's 4 minus 14 plus 10. That's negative 10 plus 10, which is 0. Let's check x equals 0. Replacing x with 0, I have 5 times 2, which is 10. Replacing x with 0 in the second expression, I have 0 squared plus 7 times 0 plus 10, which equals 10. I'm getting the same value. When x equals 1, I have 1 plus 5, that's 6, times 1 plus 2, that's 3, that equals 18. When x equals 1 in the second expression, I have 1 squared plus 7 times 1 plus 10, that's 1 plus 7 plus 10, which is 18. So I haven't proven that these expressions are equivalent, but I've tried for a few different values of x, and I keep getting the same value in both expressions. I feel pretty good about the fact that these two expressions are equivalent. Before I leave this example, I just want to say one thing about x equals 0. When I evaluated these two expressions for x equals 0, I was really only checking that I had the right value of the constant term here. So if I was going to do a check just to confirm that these two expressions were equivalent, I would choose several values of x, not just something like x equals 0, which is easy to do arithmetic with. So let's do this again. We're going to find the product of two binomials using the distributive property twice. So I have 2x minus 5, and I'm going to multiply it by x plus 3. So my first factor now is 2x minus 5, and I'm going to multiply it by each term in the second binomial. So I have 2x minus 5 times x plus 2x minus 5 times 3. Using the distributive property a second time, x times 2x minus 5 gives me 2x squared minus 5x. 3 times 2x minus 5 gives me 6x minus 15. I ended up with two like terms, the opposite of 5x and positive 6x. Combining the like terms, I have 2x squared plus x minus 15. Let's do it again. This time I'm going to do it a little bit differently. I have two binomials, and this time I'm going to distribute from right to left. We did this a little bit earlier in the lesson. I'm going to multiply x cubed plus 4x squared by the two terms in the first factor. So I'm going to have 5 times x cubed plus 4x squared minus x times x cubed plus 4x squared. Using the distributive property a second time, I end up with 5x cubed plus 20x squared minus x to the fourth minus 4x cubed. There are a lot of terms here. In a lot of these problems, we'd like to write our simplified result in descending powers of the variable. And when we do this, when we start working our way down, we can check to see if we have any like terms. The largest degree term is the opposite of x to the fourth degree term. There's only one of those. I'm going to write that first. Now I'm looking for third degree terms. I have 5x cubed and I also have negative 4x cubed. Combining those terms leaves me with just 1x cubed. How about second degree terms? There is one. 20x squared. I've combined the only two like terms I had, and now I have this product simplified. So now I want to talk about a shortcut for multiplying binomials. We've been using the distributive property twice, but there's a shortcut we can use so we don't really have to think about that every time we do it. Here's the problem we worked a couple of slides ago. The quantity x plus 5 times the quantity x plus 2. And here are the first couple of steps after we've used the distributive property twice. I want to point something out here. Look at this x squared. This x squared was the product of the first terms. I can remember that with the letter f. The next term in my product, 5x, is the product of the inside terms, the 5 and the x. I can remember inside with the letter I. The 2x is the product of the outside terms, the x and the 2. I can remember that with the letter O. Finally, the 10 is the product of the last terms, 5 times 2. I can remember that with the letter L. Now all is well and good here, except the word feel doesn't really mean anything to me. Fortunately, addition is commutative, and I can rewrite x squared plus 5x plus 2x plus 10 as x squared plus 2x plus 5x plus 10. I've switched the position of the inside and outside terms, and now I have an English word that I can remember, which is FOIL. So to remember how to multiply binomials, we remember that we're looking at the sum of the product of the first terms, outside terms, inside terms, and last terms. So let's use FOIL to find the product of some binomials. This is a problem we did earlier. Now I'm going to use FOIL. We want to check that we get the same thing that we got when we used the distributive property twice. So 2x minus 5 times the binomial x plus 3. I'm going to start by looking at the product of the first terms in each binomial. 2x times x. That's the product of the first terms. Now I'm going to add the product of the outside terms. 2x times 3. Then I'm going to add the product of the inside terms. Negative 5 times x. And finally, I'll add the product of the last terms, which is negative 5 times 3. Simplifying, I have 2x squared plus 6x minus 5x minus 15. Combining like terms, 2x squared plus x minus 15. Let's check to see if this is the same result we got when we multiplied these two binomials using the distributive property. 2x squared plus x minus 15. So this shortcut is working. So let's use FOIL again to find the product of 3x plus 1 times the binomial x minus 6. Starting with the product of the first terms, I have 3x times x. Now let's look at the product of the outside terms. I'm going to add the product of 3x and negative 6. Product of the inside terms, that's 1 times x. Finally, adding the product of the last terms, that's 1 times negative 6. Simplifying, I have 3x squared. Now I have 3x times negative 6, that's negative 18x. Adding negative 18x is minus 18x, plus x minus 6. Combining like terms, 3x squared minus 17x minus 6. Same problem. We're going to use FOIL again to help us find this product. So the product of the first terms, 1/4 x times 1. That's just 1/4 x. Product of the outside terms, 1/4 x times the opposite of x. Coefficient's going to be negative. I'll have negative 1/4 x squared. Product of the inside terms, that's just 3 times 1. That's plus 3. Finally, the product of the last terms, 3 times the opposite of x, that's giving me negative 3 times x, which when I add it, I can write as minus 3x. Now let's write this in descending powers of the variable and look for like terms. The highest order term I have is the second degree term, negative 1/4 x squared. I have two first degree terms, 1/4 x and minus 3x. I'm going to have to combine like terms, so I'm going to write negative 3 as negative 12 over 4x. Finally, my constant term is plus 3. Combining like terms, I only have one second degree term, 1/4 x minus 12/4 x, that's minus 11/4 x plus 3. One last example. 2x plus 3 times 2x minus 3. Steve's going to talk about products like this in a little bit more detail, but we tend to call binomials like this conjugates. But I'll let Steve talk about that in a few minutes. I'm just going to use FOIL here. The product of the first terms, 2x times 2x, product of the outside terms, minus 3 times 2x, product of the inside terms, plus 3 times 2x, and finally the product of the last terms, 3 times the opposite of 3. I'll be adding negative 9. So I have 4x squared minus 6x plus 6x minus 9. Look what happens to the first degree terms. They cancel. Negative 6x plus 6x is 0. And we're just left with two terms, minus 4x squared minus 9. To summarize this strategy, this FOIL shortcut can be used when we're multiplying binomials. This shortcut only works when we're looking at the product of two binomials. The product of binomials is the sum of the following products. F stands for the product of the first terms. O stands for the product of the outside terms. I, product of the inside terms, and L, the product of the last terms. The important thing to remember is that you're looking at the sum of these four products. Let's just do one more example to practice this strategy. 3x to the square plus 1 times 4 minus 2x cubed. I have a second degree binomial times a third degree binomial. Here I'm just going to write out all the steps. Product of the first terms, 3x squared times 4. Product of the outer terms, 3x squared times the opposite of 2x cubed. Product of the inside terms, 1 times 4 is 4. And finally, the product of the last terms, 1 times the opposite of 2x cubed. That would just give me minus 2x cubed. 3x squared times 4, that's 12x squared. 3x squared times negative 2 times x cubed gives me a coefficient of negative 6. So I'm adding negative 6, x to the 5th. X squared times x cubed, x to the 5th. Plus 4 minus 2x cubed. Now at this stage, I'm really done. There are no like terms. I have a second degree term, a fifth degree term, a 0 degree term, and a third degree term. I could, though, rewrite this in descending powers of the variable. Often the answer in the back of the book when you're checking your work is what the polynomials are given in descending powers of the variable. So I'm just going to do that. The important thing is that you recognize that these two expressions are equivalent. My highest power of x is x to the fifth. I have an x cubed term. I have an x squared term. I have no x term, but I do have a constant term. With that, I'm going to turn it over to Steve, who's going to look at more examples of products.
Hello. As Anne promised, I'm going to talk more about polynomial multiplication. I'm going to begin with some examples of what we call special products. And then I'm going to work some multiplication problems involving polynomials with more than two terms. So let's begin with special products. One type of special product is the square of a binomial. And a lot of people, when they look at a problem like x plus 4 quantity squared, they immediately jump to the conclusion that that's just going to be x squared plus 4 squared, or equivalently x squared plus 16. Let's show that that is a wrong conclusion to jump to. Let's show that these two expressions are in fact not equivalent. And we can do that if we can find any one value of x for which the two expressions have different values. Let's try x equals 1. If x equals 1, then the expression x plus 4 quantity squared becomes 1 plus 4 quantity squared. That's 5 squared, which is 25. On the other hand, the expression x squared plus 16 becomes 1 squared plus 16, which is 17, but more to the point, it ain't 25. When we replace x with 1, x plus 4 quantity squared and x squared plus 16 are not equal to one another. Consequently, the two expressions are not equivalent. Let's make note that had we chosen to replace x with 0, we would have gotten the same number for both of the expressions. 4 squared is 16. 0 plus 16 is 16. 0 is not a good number to use when you're trying to check whether two expressions are equivalent or not, because you will frequently get a false true reading. What's the fundamental problem with thinking that x plus 4 squared equals x squared plus 16? It's thinking that exponents distribute over sums. Recall that exponents distribute over products. Exponents do not distribute over sums or differences. Alrighty, we've seen what x plus 4 quantity squared doesn't equal. Let's figure out what x plus 4 quantity squared does equal. Before I actually go ahead and find the simplification of x plus 4 squared, I want to look at the directions for this specific problem. It says expand and simplify x plus 4 quantity squared. Finding the product of two or more polynomials is often called expanding the expression. So what are our two polynomials? Well, what does an exponent of 2 mean? It means to multiply together two factors of the base. The base here is x plus 4. So we need to multiply together two factors of x plus 4. Finding this product is called expanding the product. Okay, let's use our FOIL acronym. Multiplying together the first terms, x times x, is x squared. Multiplying together the outside terms, x times 4, is equivalent to plus 4x. Multiplying together the inside terms, 4 times x is also 4x, and multiplying the last terms, 4 times 4, is plus 16. Then when we add our like terms, this simplifies to x squared plus 8x plus 16. Remember, on the last screen, when we replaced x with 1 in x plus 4 quantity squared, we got 5 squared, which is 25. What do we get when we replace x with 1 in this trinomial here? 1 squared is 1, 8 times 1 is 8, 1 plus 8 is 9, plus 16 is 25. This time the expressions are equivalent when x is 1, and in fact they're equivalent for all values of x. Now one more thing before I leave this slide. Let's notice that our outside product was 4x and our inside product was also 4x. The outside and the inside were the same. Is this always the case when we multiply the square of a binomial? Well, let's check it out. This time, let's multiply together the square of a binomial difference, a minus b quantity squared. Recall that this means that we need to multiply together two factors of a minus b. Let's use FOIL. Let's begin with our first terms. When you're multiplying together binomials, you need to make sure that you consider the sign of the terms as well as the absolute value of the terms. In the product of the first terms, we have positive a times positive a. That is positive a squared. On the outside terms, we're multiplying together positive a and the opposite of b. The result is going to be the opposite of a times b. Inside terms, that's the opposite of b times positive a, so that gives us the opposite of ba. And the last terms, opposite b times opposite b gives us positive b squared. Now looking at my outside product and my inside product, they both have factors of a and b. Let's go ahead and compute the b and a in the inside product term so that it is also ab just like the outside term. Now when I combine my like terms, I get the product a squared minus 2ab plus b squared. If instead of multiplying the square of a minus b, I had multiplied the square of a plus b, I would have gotten something very similar. The only difference is the inside term and the outside term would add to plus 2ab rather than minus 2ab. I'm going to ask you to do me a favor. Please memorize these two formulas. The reason why I want you to memorize these two formulas is because one of the most common mistakes people make in algebra is when they're squaring a binomial, they just square the first term and the last term and either find the sum or difference. If you memorize these formulas, you're less likely to make that mistake because you'll know that you need 3 terms in the product, not 2 terms. Let's go ahead and use our new formula. Let's expand and simplify t to the 5th plus 4 quantity squared. Now recall that that exponent of 2 means that we need to multiply together 2 factors of t to the 5th plus 4. And we could do that using FOIL. There'd be nothing wrong with that. But I'm going to use our new formula because I'm encouraging you to memorize this formula. So let's identify what's a and b. A is t to the 5th and b is 4. So let's apply the formula. We have t to the 5th plus 4 quantity squared. According to my formula, that's my a, which is t to the 5th quantity squared, plus 2 times my a, which is t to the 5th, times my b, which is 4, plus my b squared. So that's plus 4 squared. T to the 5th squared. Do you remember what that's called? It's called a power to a power. And the power to the power rule says we need to multiply together the exponents. 2 times we have 5 factors of t. So altogether we have 2 times 5 factors of t, which is t to the 10th. In my middle term, multiplying together 2 and 4, I get a coefficient of 8, and I have my t to the 5th factor, and then plus 4 squared is plus 16. Now notice that I have cleverly put my formula in a little thought bubble because eventually you want to just memorize this formula and apply it from memory. But I strongly suggest the first several times you work problems like this, you actually write the formula onto your paper before applying it. And you know what? If it turns out that that's the only way that you can be successful with this formula, that's great. Always write down the formula, but do make sure that you memorize the formula so that you'll be able to write it down when you need it. Let's expand and simplify 11 minus 3y squared quantity squared. Checking out the old noggin, I remember first that I need to multiply together 2 factors of 11 minus 3y squared, And then I remember that I have a special formula for doing this product. A minus b quantity squared is a squared minus 2ab plus b squared. The first few times you work these problems, you might want to write down what a and b are. In this example, a is 11 and b is 3y squared. Notice that I put that in my thought bubble. Eventually, you want to be able to keep track of this in your head, if at all possible. But at first, it is a good idea to write it down. Now let's apply the formula. We have 11 minus 3y squared, quantity squared. That's going to be our a squared, so that's 11 squared. Then we have minus 2 times a, which is 11, times b, which is 3y squared. And then we have plus our b, which is 3y squared, quantity squared. 11 squared, that's 121. The coefficient on the middle term, negative 2 times 11 times 3 is negative 66, and that's multiplied by y squared. Do you remember what this last term's called? It's called a product to a power, and exponents distribute over products. I can write this last term as 3 squared times y squared squared. So ultimately, this simplifies to 121 minus 66y squared. 3 squared is plus 9. Y squared squared, that's a power to a power. I need to multiply the exponents. That gives me y to the 4th. Now, generally, I would never write this step down. The only reason I wrote this step down in this example was I just wanted to remind you the way the product to a power rule works. Now we're looking at a different type of product, a plus b times a minus b. First thing we're going to do is apply FOIL. The product of the first terms is a times a, which is a squared. The product of the outside terms is positive a times opposite b, which is opposite ab. The product of the inside terms is positive b times positive a, which is plus ba. And the product of the last terms is positive b times opposite b, which is opposite b squared. Just like when we squared binomials, the outside product and the inside product are like terms. We can take that BA, apply the commutative property of multiplication, and rewrite it as AB. But this time, something very different is happening. The outside product is minus AB, the inside product is plus AB. The outside and the inside, they're adding to 0. And I'm just left with what we call a difference of squares. A squared minus b squared. A little vocabulary for you. The binomials a plus b and a minus b are called conjugates. And there's a property of conjugates. Conjugates always multiply to a difference of squares. Wordy people sometimes refer to conjugates as the sum and difference of two terms. There's a little problem with this reference though. Even though by definition terms are added, so there is no such thing as a difference of terms. So when you hear somebody call conjugates the sum and difference of two terms, you need to not take them too literally. They're using the word term in a more figurative sort of way. Let's expand and simplify x plus 5 times x minus 5. When you see problems like this, you want to remind yourselves that these two binomials are called conjugates. And then you need to recall that conjugates multiply to a difference of squares. In this example, our a is just x, and our b is just 5. So x plus 5 times x minus 5 multiplies to x squared minus 5 squared, which is x squared minus 25. All right, let's multiply 14 minus 5t to the 7th by its conjugate. Well, we need to first identify what the conjugate is. The word conjugate only applies to binomials. And to find the conjugate of a binomial, what you need to do is change the operation between the monomials at the beginning and end of the binomial. Since I have subtraction in the given binomial, the conjugate is going to have addition in the middle. So I'm going to multiply 14 minus 5t to the 7th by 14 plus 5t to the 7th. This time, I'm going to try and use the formula really in my head. The product of conjugates is a squared minus b squared. A is the monomial before the operation. In this case, that's 14. So this is going to give me 14 squared. Minus b is the monomial after the operation, which in this case is 5t to the 7th. So I need to subtract 5t to the 7th squared. 14 squared is 196. Distributing the exponent of 2 over the product 5t to the 7th, I get 5 squared, which is 25, and t to the 7th squared, which is t to the 14th. You know what? After you've worked lots and lots and lots of practice problems, you might be able to write this down without even writing this step down. You might experiment and see if you can have success that way. If you can, great. If you're not as successful that way, that's great too. Just go ahead and write down however many steps you need to write down so that you are successful. But I do suggest that you at least try to leave out some of the steps, because how else will you ever know if you can be successful without writing all the steps unless you try? Let's find the square of 14 minus 5t to the 7th. This time, we want to take our expression and square it. So rather than multiplying our original expression by its conjugate, we're going to multiply our original expression by another factor of our original expression. Do you remember the formula here? The formula for the square of a binomial difference says that we need to square the a, so that's going to be 14 squared, and then we need to subtract 2 times the a times the b. The b here is 5t to the 7th, and then we need to add the b, which is 5t to the 7th, quantity squared. So what do I get? I get 196. 2 times 14 times 5, that seems pretty tricky to me, but if I commute the factors and think of it as 2 times 5 times 14, that's not so tricky. 2 times 5 is 10, times 14 is 140, so my coefficient is minus 140, that's times t to the 7th, and then plus 5 squared, which is 25, times t to the 7th squared, which is t to the 14th. Now let's talk about multiplying together polynomials when at least one of the polynomials has more than 2 terms. We're going to begin with the example a plus b, that binomial, multiplied by the trinomial x plus y plus z. The first thing that we need to toss out the window is FOIL, F-O-I-L. You can only apply FOIL when you're multiplying together 2 binomials. Since we have a trinomial here, we need a new strategy. Now, before I begin this problem, the use of the letters here may suggest to you that I'm going to be coming up with some kind of formula. That's not what I'm doing. The reason why I'm using 5 distinct letters is just so that it's as easy as possible for you to keep track of what's what when I do the expansion. The first thing I'm going to do is I'm going to take the trinomial x plus y plus z, and I am going to distribute it over the 2 terms in the binomial. So I'm going to take the trinomial x plus y plus z, and I'm going to multiply it by the a term. And that gives me a times x plus y plus z. Now thinking ahead, let's notice what the net effect is going to be when I get to my final step. A is going to have to be distributed to x, to y, and to z. In other words, the a term is going to be multiplied by every single term in the trinomial. Now I also need to distribute the trinomial x plus y plus z to the b term. Notice here the net effect is that b is going to be distributed to x, to y, and to z. So what's the upshot? The upshot is that every term in the binomial is multiplied by every term in the trinomial. Let's notice that since there were 2 terms in the binomial and 3 terms in the trinomial, in the product I had 6 terms. And it turns out that before simplification, the number of terms in the product of 2 polynomials is the product of the number of terms in each polynomial. Now I think that's a pretty polysyllabic property, so let's see an example of what all those words mean. Suppose that we wanted to multiply together x to the 4th plus x cubed minus x squared plus x minus 9 and x cubed minus x squared plus x plus 7. Well, the first polynomial factor has 5 terms, and the second polynomial factor has 4 terms. So before we got to our simplification step, the number of terms in the product would be 5 times 4 terms, which is 20 terms. So one thing is for sure, and that's that I'm glad that I'm not going to actually work this example. Let's work this little bit less complicated example. Let's find the product of x minus 4 and x squared plus 3x minus 8. Another way of saying that is let's expand and simplify this product. So I'm going to begin by taking the first term of the binomial, which is x, and I'm going to distribute it to every term in the trinomial. So I'm going to write out what I'm finding, which is x minus 4 times x squared plus 3x minus 8. And the first product I'm going to find is x multiplied by x squared. That's x cubed. Now I'm going to multiply x with plus 3x. That's plus 3x squared. Now I'm going to multiply x with minus 8. That's minus 8x. I'm done distributing the x. Now let's distribute the minus 4. Minus 4 times x squared is minus 4x squared. Minus 4 times plus 3x is minus 12x. And minus 4 times minus 8 is plus 32. Now I need to combine my like terms. It helps when combining your like terms if you write your powers of x in descending order. So the highest power of x I have here is x cubed, and there is only one x cubed term. I'm going to go ahead and check off that I've accounted for the x cubed term. You might want to lightly cross out x cubed to note that you've accounted for the x cubed term. Now let's look for x squared terms. Here's a 3x squared, here's a minus 4x squared. Altogether I have minus x squared. How about linear terms, first degree terms? Minus 8x, minus 12x, that's minus 20x, and all I have left is my constant term, which is plus 32. Alrighty, let's expand and simplify t to the 4th minus 3t minus 4 times 1 minus t. Remember that I need to distribute every term in the trinomial over every term in the binomial. So let's go ahead and do that. T to the 4th times 1 is t to the 4th. T to the 4th times minus t is minus t to the 5th. Minus 3t times 1 is minus 3t. Minus 3t times minus t is plus 3t squared. Minus 4 times 1 is minus 4, and minus 4 times minus t is plus 4t. Let's look for like terms. Something that can help you find like terms is if when you write your final simplification, you focus on descending powers of the variable, which in this case is t. The highest power of t is t to the 5th. I have opposite t to the 5th. Let's look for t to the 4ths. There's one of them, specifically 1 t to the 4th. How about t cubes? There's no t cubes. T squareds, sure enough, we have plus 3t squared. T factors, well, there's a minus 3t, a plus 4t, so that's plus t. and then we have minus 4. In this example, I'm going to show you a different organizational strategy. The last two examples, I've worked horizontally. This one, I'm going to work vertically. But before I do this specific problem, I'm going to remind you of a method that you learned for multiplying together two numbers with several digits. Let's look at the product of 211 with 35. We began by distributing the 5 over each of the digits in the 211. We went 5 times 1, which is 5, 5 times 1, which is 5, and then 5 times 2, which is 10. Then, when we distributed the 3 over each of the digits, we shifted to the left one place, and we reminded ourselves to do that using a 0. Then, distributing the 3 to the 1, we get a 3. Distributing the 3 to the next one, we get a 3, and 3 times 2 is 6. And then we went ahead and added up the results, 5, 8, 3, and 7. We're going to do something similar with our two polynomials. So to begin, we're going to go ahead and write our trinomial on top and our binomial on the bottom. And the first thing we're going to do is we're going to distribute the negative 5 over the 3 terms of the trinomial. We're going to take 2y cubed plus 3y minus 4 and multiply it by negative 5. Let's go ahead and do that. Negative 5 times negative 4 is plus 20. Negative 5 times 3y is minus 15y. Negative 5 times 2y cubed is minus 10y cubed. Notice that we skipped y squared. In that arithmetic example I showed you, something similar happened. We multiplied 5 and 2 and got 10, and we saved a place for the hundredths digit by writing a 0. What I'm going to do is I'm going to save a place for a squared term by just leaving a little bit of a gap, and I'm going to write minus 10y cubed over here. And the reason I'm doing that is it's very possible that when I distribute the 7y to the trinomial that I will in fact end up with a squared term. Let's do that. 7y times negative 4 is minus 28y. Notice that my first term was jogged left, just like it was when I multiplied together two numbers. 7y times 3y is plus 21y squared. It's a good thing I saved myself a place to write a squared term. 7y times 2y cubed, that is 14y to the 4th. I don't want to write that underneath my cubed term because those two terms won't combine. So I'm going to go ahead and move even farther left and write my 14y to the 4th. Look at something that's kind of swell about this method. It's easy to identify my like terms because they're all lined up. I have 14y to the 4th minus 10y cubed plus 21y squared minus 43y plus 20. Alrighty, let's expand and simplify x minus 3 times x squared plus 3x plus 9. I could go ahead and write the binomial on top and the trinomial on the bottom. But if I do that, I'm going to have to distribute the 9 to the binomial, the 3x to the binomial, and the x squared to the binomial. I'm going to get 3 rows of work. I think it'll be a little easier to organize my work if I write the trinomial on top, because then I only need to do 2 distributions, which will give me 2 rows. So let's go ahead and do that. Negative 3 times 9 is minus 27. Negative 3 times 3x is minus 9x. Negative 3 times x squared is minus 3x squared. Let's distribute the x through the trinomial. X times 9 is plus 9x. X times 3x is plus 3x squared. And x times x squared is x cubed. Something interesting seems to be developing here. I have an x cubed, but then my x squared terms, they add to 0, as do my linear terms. All I'm left with is my lonely little x cubed, and then my minus 27. Now I'm seeing a pretty big gap between x cubed and minus 27, so I think I'm going to go ahead and write a little more formal conclusion here. that x minus 3 times x squared plus 3x plus 9 simplifies to the weeny little binomial x cubed minus 27. Now, let's remember where the 27 came from. That came from 3 times 9, which is 3 times 3 times 3, which is 3 cubed. X cubed minus 27 is called a difference of cubes, and this is something we're going to be talking about in quite a bit later on in the term. Let's multiply these two trinomials. X squared plus x minus 3 multiplied by 2x squared minus 4x minus 7. The first thing I'm going to do is I'm going to take that second trinomial, 2x squared minus 4x minus 7, and I'm going to distribute it over the three terms in the first trinomial. I'm going to take x squared times the second trinomial plus x times the second trinomial minus 3 times the second trinomial. Now notice when I get to the next step, the net effect is that x squared from the first trinomial is going to be distributed to every term in the second trinomial. Similarly, x from the first trinomial is going to be distributed to every term in the second trinomial, and likewise, negative 3 needs to be distributed through the second trinomial. I'm just going to go ahead and do those three distributions. So I'm going to begin with x squared plus x minus 3 multiplied by 2x squared minus 4x minus 7. And the first thing I'm going to do is I'm going to distribute x squared through the second trinomial. X squared times 2x squared is going to give me 2x to the fourth. X squared times minus 4x is going to give me minus 4x cubed. X squared times minus 7 gives me minus 7x squared. Now let's distribute the x through the second trinomial. X times 2x squared is plus 2x cubed. X times minus 4x is minus 4x squared. X times minus 7 is minus 7x. Now let's distribute negative 3 through the second trinomial. Negative 3 times 2x squared is minus 6x squared. Negative 3 times minus 4x is plus 12x. Negative 3 times negative 7 is plus 21. Let's go ahead and combine our like terms. X to the fourth is the biggest power of x, and there's only one x to the fourth term, 2x to the fourth. Minus 4x cubed plus 2x cubed gives me minus 2x cubed. Minus 7x squared minus 4x squared minus 6x squared, that's a whole lot of minus x squared, specifically minus 17x squareds. Linear terms, minus 7x plus 12x, that's plus 5x, and then we have our constant term plus 21. You know what? There was a whole lot to keep track of there. I think this problem might have been a little bit easier if we had used the vertical method. Okay, so I've gone ahead and had the computer set me up for the vertical method. I wrote the first trinomial over the second trinomial. Let's begin by distributing negative 7 over all the terms in the first trinomial. That's going to give me plus 21 minus 7x and minus 7x squared. Now let's distribute minus 4x over every term in the first trinomial. Minus 4x times minus 3 gives me plus 12x. Minus 4x times x gives me minus 4x squared, and minus 4x times x squared gives me minus 4x cubed. Now let's distribute 2x squared over every term in the first trinomial. 2x squared times minus 3 gives me minus 6x squared. 2x squared times x gives me plus 2x cubed, and 2x squared times x squared gives me 2x to the fourth. Adding up my like terms, which are all nice and lined up for me, I get 2x to the fourth minus 2x cubed minus 17x squared plus 5x plus 21. And I don't know about you, but I think it was much easier to organize this work vertically than it was horizontally. And that ends my part of the lesson. What Candace is going to introduce to you is mixing up polynomials that have more than one variable.